Hi, I'm Liz. I'm a first year PhD student in astronomy, and this is the first paper review that I decided to record. And it's going to be on this paper called How Large is a Disk? What do protoplanetary disk gas sizes really mean? And I chose it because I'm currently in the process of answering to review to my paper, and this work is kind of really relevant to what we do in that paper. So I was just reading it related to that and decided to do a full-blown review since I read it anyway. So, and I will give a bit of a more bit of a simpler introduction than there is in the paper, because even though these reviews are intended for colleagues, I can imagine that it can attract a pretty wide range of fields. So when we go about disk sizes, there are two different approaches based on whether you're a modeler or an observer. And first I will touch on the modeling side. And in our models, what we typically do is to describe the density distribution, we use this prescription for surface density. This is its dependence on radius, and it has this characteristic called characteristic radius. Yeah, I know. And this is kind of the main thing that determines the disk size. And by disk size, I mean the position of the density isosurface. Like, for example, if you take some value of density and track where it is reaches the midplane, that you would consider a size. And the characteristic radius is the main factor in determining this position. It also obviously depends on other stuff, like for example on gamma, which kind of determines the steepness of the power, or basically what parts of the disk have more mass, whether it's more concentrated towards the inner parts or outer parts, or maybe the same everywhere. Also depends on this normalizing coefficient, where basically disk mass resides. Obviously this isosurface depends on all that, but the main factor in this position is considered to be characteristic radius, and for modelers this characteristic radius is synonymous with our understanding of size. The formula itself comes from these papers, where it's basically just a theoretical result for a viscously evolving disk. And by that we mean that there is a disk of gas which rotates with different speeds at different radiuses, and it kind of creates some friction, which creates some radial drift towards the star, but at the same time the disk expands to conserve the angular momentum, and this is what creates this tapered power law. It's result applicable not only to protoplanetary disks, it's true for any viscous accreting disks, and in the Lynden-Bell paper they consider a wide range of applications. In Hartmann they consider it applied only to protoplanetary disks. But when we go to observations, obviously you don't measure any characteristic radius, it's a purely modeling parameter. So instead what they can do directly with observations is they can measure the areas in their intensity maps where a certain percentage of flux resides. And this is the main value that they deal with and understand as a size. So for example, here I have a few intensity maps, and let's look at the top left. This is an intensity map in CO line transition 2 to 1, rotational transition 2 to 1 of a disk in loop. This is from one of the MAPS papers. MAPS is a large program on ALMA telescope. And what you do is well, there are different ways to determine R90, but like a very primitive one is that you just draw regions of different radiuses and see how much flux is inside of them, and when it gets to the 90, the radius of this area is your size. But the thing with this observational size, which is obviously very direct, very obvious measure, is that it is different because what observations? The question is what intensity map on what wavelength, and it is true, and you can see that by looking at other panels, that the R90 for CO to 1 and C17O 1 to 0 are very different, and it is also different for dust continuum emission. And you can see that there are different scales. So for example, this scale, so like this image is 10 arc seconds wide, this is 4 arc seconds wide. So disk in the dust is much smaller than the gas disk in CO. So observations have this problem. They don't have one size, they have a range of sizes that can be measured for different lines or at different wavelengths in continuum. And what is typically done is that it is typically measured in two ways. So the first one is this CO transition. Why? Because CO is the second most abundant molecule after molecular hydrogen, but molecular hydrogen we can't directly observe because it has very high energy transitions. You need to go into UV, and it is optically thick, so what you see in this transition is just the surface of the disk, and it is considered to be well mixed with gas, so it is considered to be tracing the gas. So you're tracing, looking into this transition, you are tracing the surface of the disk, and therefore it is considered to be a good measure of the gas component of the disk. But also dust component is not forgotten as well, because this is its own thing, and you can see that it's definitely a drastically different size, and it holds its own information. Obviously the sizes and other transitions and wavelengths can be analyzed, and it can be an interesting kind of analysis exercise to see how this thing changes from line to line and what it can tell you, because it can tell you stuff. But typically, if you want to determine the size, you go for the size of the gas component, you go to CO. If you want to determine the dust component, you go to a certain wavelength of dust continuum. You can choose different ones, and it will kind of trace different dust sizes. That's the idea. So you can see the problem here is that when we talk about disk sizes, and I don't need to convince you why size is important. Humans measure everything, including disks, and we want to know their sizes. Modelers and observers operate in very different terms. Modulars have this characteristic radius RC, modulars have this radius R90. And the idea of this paper is try to find the connection between them. How? Basically, they take a model that has some a chemical model that can determine CO abundance according to the inputs that are given, and then they can simulate the observations of a certain CO line, and then with this from these simulated observations they can get an R90. So you have a model with non-parameters and R90 that it gives you, so you have both RC and R90, and from that you can try to find some correlations and dependencies and establish the connection between them. That's the idea. Very, very simple. So how do they do that? Well, first, what is their model? So they use the so-called DALI model. This is an abbreviation. I don't remember what it means. Something dust and lines, something, I think. Never mind, it doesn't matter what it does. So it has it calculates self-consistently thermal and chemical structure for a given density structure and radiation field. So what does it mean? You give as an input how mass is distributed in space. You give the star, you give the interstellar radiation field, and first it solves with a Monte Carlo radiator transfer dust temperature, and with the dust temperature as an input it serves self-consistently chemistry and gas temperature, because chemistry is a part of the thermal balance for gas, and that's the result. What is their density structure? So for surface density they use the same prescription that I showed you before, only that there is this normalizing component. Normalizing term is expanded. Here you see the M disk sitting as I mentioned before. And one difference from the formula that I showed is that they also add this Xi in the exponent. This is basically to account for also wind-driven evolution. It's when basically magnetic fields create winds of particles that go away from the disk, and this is also a way to eliminate or a way to increase angular momentum so that stuff can accrete onto the star. And but on the modeling, in the modeling sense, this is just decouples these two exponents, and that's it. But there is physics behind it, trust me. And for vertical structure they use this Gaussian prescription of it. So there's the formula, it's just yeah, there's just Gaussian dependence on Z with dispersion in the form of a so-called scale height, and the scale height is itself consists of two parameters hc and psi that you just set up for a given disk. This formula comes from considering hydrostatic equilibrium, basically when your gravity is what's the right word? No. God. Why the words escape my mind? Equalized by pressure. So gravity equalized by pressure of the gas. But but it is derived, this exact formula is derived in isothermal approximation, basically when you can think that along the vertical axis your temperature is constant. It is not true, but people typically, when in the models where you calculate temperature using radiative transfer, people choose to use that because otherwise you would need to solve density in thermal structure self-consistently through iterations. And if you consider inner disks in your model where the stuff is optically thick, where it's so dense that it's optically thick to stellar emission, it might lead to some seesaw density structure, and I've dealt with it. There is no neat way to resolve it. There is kind of a way to resolve it through doing, for example, diffusion approximation as post-processing. It smooths the results a bit, but does not give a very satisfactory result, in my opinion, if it's really optically thick. So that's why people, to avoid these iterations, to also self-consistently solve for that, they just prescribe the vertical density structure and forget about it. But I do have to note that the temperature structure that is calculated for this prescribed density structure, they are not they're not self-consistent. They're not. If you start considering real hydrostatic equilibrium, it will converge to a very different one. Anyway, that's that. Then they also consider, as for dust, they consider two populations of grains, small and large, and they have different portions of total dust mass assigned to them. This is described with this F large. So 90% of mass is in large grains, for example, but large grains have a different scale height. Basically, the scale height for large grains is multiplied here by by this value. For the star, they have a star with 4000 K effective temperature and luminosity. They consider a range of it. And they also have an accretion source, like a central source of luminosity that comes from accretion. It has an effective temperature of 10,000 Kelvin and a mass accretion rate of 10 to the minus 8. All very classic values. And these values can be converted to luminosity. And they have chemistries, you can notice, and they promote this model as a thermochemical model. But in this particular paper, I have not found a single mention of what chemistry there is in this model. There is not even a word reaction in the paper, which I find weird. So I don't know what kind of chemistry is there. Is this important? Now, CO, this particular transition of CO that they choose is, as I said, optically thick. It traces the surface. So it might not really be important what goes under there, right? Especially if they don't have any dynamics in the system that can transport stuff from, for example, beneath to up, the so-called vertical mixing. And they don't have that. But if you look at the M gas here, they go to such low masses as even 5 to the 10 to the minus 7. And this is a very low mass for a disk. And for such low mass disks, they are transparent in CO. I checked. I ran a model specifically to test that. And it's optically thin. You can see the whole disk. I ran even like, no, I ran 5 multiplied by 10 to the minus 6, because 5 multiplied by 10 to the minus 7, I couldn't even start on our model. It just complained that it's so low mass. And I don't even know if such disks can be observed, like basically detected, because they're so diluted. But for a fact, you can see the entirety of disk for such low mass. And this is where the chemistry is important, obviously, because you have the entirety of a disk. Why they chose not to tell us the chemistry, I don't know. But it is what it is. And here's a table, yes, of all the model parameters that they chose to report. And they consider a range of models, and they first consider models with all parameters fixed by but M gas, and those and for those parameters that have several values, you see for this set of models the relevant values in bold. So the first run several models with different M gas, but these values that are in bold, and then they also run some models with different values from these brackets to basically test how their results are robust against the changes of the parameters. And I think now it's time for results. And what they do, there are several plots. First, let's look at the top left. What they show us here is the dependence of the value called N gas at the position of R90 and how this depends on mass of the disk. What is N gas? N gas is basically just surface density. Yes, is it? Yes, I got confused about the term. I felt like it needed another word, but no. So surface density. This is basically a value of surface density just divided by 2.3 masses of proton, which is a mean molecular weight. Basically, surface density divided by mean, the weight of a mean molecule in the gas. So basically this is surface density at the obtained R90 for the models weighted against mass of the disk of the model. And what they find is that for most of the models they are neatly aligned along this approximation where N gas is proportional to M disk to the power of 0.34. Though, as you may notice, it breaks for larger disks. So 10 to the minus 1, 10 to the minus 2, with like those kind of waves going on, some weirdness here that are not well described by this. And I want to know that 10 to the minus 3 to 10 to the minus 1, I would consider actually the masses of relevance. This is the masses that we see, that we can detect. And this is the area that's kind of relevant for us on the observational level. Like, we know about these disks. And yet they base this approximation on mostly low mass disks. That's a choice. Okay. Then the top low left panel, they show the column density for CO at the same location. So basically it's they, I suppose, have, this is a 2D model, they have a distribution of CO abundance in the disk in each cell. They multiply it by N gas and integrate it over Z, you get NCO. So that's not surface density, this is the result of chemistry, and you see here that it kind of turns into this arch. And if you divide it by N gas, you get the bottom right figure, which is essentially a column averaged CO abundance. And you see that it falls with mass. The reason for that is kind of here in the top right figure, where they show Z freeze as it depends on disk mass. And that Z freeze is a location of the temperature 20 Kelvin at the radius of R90. They don't write R90 here, but this is also supposed to be at R90 because everything here is R90. And 20 Kelvin is considered to be like this classic freeze out temperature for CO. So basically at Z below the Z freeze, you would expect CO to be completely in the ice phase and not emitting, although you don't see it in this. Although, I mean, I guess for lower mass disks you see that. So for lowest mass disks, there is even a question if this area exists, because they're so low density. I suppose that the star just shines right through it. I'm sorry if that was, never mind. But as you increase mass, Z freeze increases, obviously because the disk is just becoming bigger and bigger, and it becomes in it's colder and colder. Again, it depends on where you look, but we'll look at R90, and I guess R90 in their models is in the area where at the mid-plane there is cold enough temperatures, which is interesting. Would that be true for our models? I'm not sure, but evidently, since they have that Z freeze at R90, unless I'm wrong, let me check real quick. I have a paper opened up because I think it should be Z at R90. Yes, it's Z at R90. So I guess well, because sorry, I'm just going off script here, but I'm just thinking about how it is in our models, and in our models this area where CO is depleted into the ice phase, though we also have grain surface chemistry, so it's depleted not only by freezing out. This place, it's kind of localized in a certain radius range, because closer to the star it's warmer, further from the star the disk gets diluted enough so that interstellar radiation field kind of doesn't allow it to get photodesorbs it, and it's not frozen out anymore, even though the temperatures there are colder, can be colder according to the model, but it's just diluted enough that the photodesorption plays a bigger role. Oh wait, but then it's just CO not frozen out. But here they yeah. I guess that's sorry. Anyway, you just see me thinking in real time. The thing is that this Z freeze, it's not actually determined by CO abundance. Like, they don't trace where CO abundance becomes like comparable to CO on ice abundance. No, this is basically a position of isoline, or of temperature isoline, which, you know, and the further from the star it is just colder, and if you increase the mass, of course it obscures the area even further, and the temperature drops even more, and therefore this area, this isoline, rises in Z. Yeah, okay, it's cleared out, because yeah, I forgot that it's not really connected to CO abundance. Silly me, though you would expect that to be connected. Sorry. Anyway, this plot is finished. Then they also compare the N gas at R90 versus M disk with different variations of parameters. So here, like, they vary one parameter and plot the results with what this one parameter varied. And what they argue is the differences, the only parameters that matter are luminosity, gamma, interstellar radiation field. Others, they say, irrelevant. And in the larger picture of this whole dependence, maybe, but if you look at again at this area of interest, or area of relevance to observations, from 10 to the minus 3 to 10 to the minus 1, you see that they actually vary for all these parameters. For psi, for f large, for he, obviously gamma, also a bit for RC. Yes, there is either existing, like there's some wiggling for 5AU. There's also some different type of wiggling for 40. For 20 there is no wiggling, or this wiggling is a bit different. So, you know, if you would enhance, if you would just focus on that part, you would actually see different behavior. So to say that other parameters can be neglected is a choice, in a way. You kind of pretend you do not see that it is something different happening here for this mass range. Okay, your paper. And I'm reviewing it. Yeah. But what's interesting, maybe we'll touch on it later. Yeah. And I actually tested it on our models because I got curious if we would reproduce it No, we do not reproduce it at all. We have a much significantly, but again, we consider only models from 10 to the minus 3 to 10 to the minus 1, and for us in that range, characteristic radius is, and star luminosity as well, are doing their own thing. It's also very important, like, because they vary only one parameter at a time, but it's also interesting to see how dependencies on parameters change under different values of parameters. Basically, like, you change the luminosity and then you vary characteristic radius. How would that change? Also interesting, but they don't do that. And for example, but I did it on our models, and luminosity of the star did change how it changes with characteristic radius. So, you know, my plot is much more messier, much more inconclusive, and yeah, not inconclusive. I wouldn't. The conclusions can be made. I just didn't analyze it further. I just saw that it's very different. Anyway, further on. So, what they get here is this approximation of dependence of N gas at R90 on M gas, right? And if you also want to consider luminosity, it modifies in that way. Weird that they noted that it depends on gamma and interstellar radiation field, but they don't include that here into the fit. Okay, I guess that's not that important. And you might ask yourself a question: why this value? Like, it's a very I would say inobvious value, because R90 itself holds chemistry in a very ambiguous way. Like, you need to really try to disentangle it, and you put it into another value, so it is even harder to disentangle its meaning. And then you get this dependence that also holds chemistry somehow, because it's evaluated at the chemically dependent value. So there is a lot of chemistry behind this, allegedly. No, not allegedly, just is. I said allegedly because we don't know what the chemistry is, unfortunately. So why? And there is a very neat idea that I like. The thing is that, again, N gas is the surface density. So you can just expand it, put that in, put instead of R90, do some algebra, and bam, you have dependence of R90 on RC and mass of the disk. This is what we wanted, the connection between them two. And this is the way to obtain it. And so they get this formula. As you remember on the previous slide, this also depends on luminosity. They provide what needs to be put into the square brackets to also have the dependence on luminosity. Again, there should have also been dependence on gamma and interstellar radiation field here. They decided to ignore it. Okay, so we don't get it. We get just this approximation. Fine. But this is like the main result of this analytic connection between R90 and RC, depending on the disk mass, and also gamma C in luminosity if you want. Okay. And this is the plot that they accompany this formula with, is basically their results, the points. So this is R90 depending on M disk. Points are their results. And orange line is the formula that we just saw. I guess assuming some gamma and xi, and also characteristic radius, I guess, for some value of characteristic radius. Probably 65. Yeah. And then there is also two other. So they more or less align, which makes sense. It's kind of a self-fulfilling prophecy, because they constructed this analytic solution on the results of their models. This is a completely modeling result, so it's good that it fits their own results. But you see these little deviations first in larger masses. I have noted why, because the whole approximation is not really valid there. And for lower masses, which I find weird, because it is actually well described by lower masses, as you can see here. Like, it's pretty much on point. Why is there a deviation? They know that there is a deviation because, as they say, it's not really well fit, but it is really well fit. I don't know what's the problem here. Anyway. And then they also compare it to green line, which is the analytic result from another paper. I haven't read that. And from the case when you kind of, in this formula, you just forget about this power law and consider only exponent, because if R90 is much bigger than characteristic radius, the exponent is what dominates the value, so you can kind of forget about the power law. But as you can see, it's not really well describing anything. Anyway, further on, and then they plot the dependence of R90 on RC, basically this analytic formula that we found, for different values of 10 to the of disk mass. And what they find is two things. First is that for a given mass, you have a maximum value of R90. And what you can do with that is basically make an estimate of a lower limit on mass for a given R90, because if for a given mass R90 must be below a certain value, that means for a given R90 mass must be above some value. And they do that. They take a derivative, they find the extremum using this analytic formula and find this limit on the disk of the mass. Again, they did that only using like certain values of gamma, xi, and luminosity. So this is, I wouldn't say that this is a universal formula, but the idea is nice, that you can kind of get an estimate on the mass disk from that. The second thing is that for each value, for a given value of R90, there are two solutions to the value of characteristic radius. There is a chemical explanation for this. It's basically just photodissociation. So if you have a fixed mass and you continue your disk, like stretch it further and further, it becomes less and less dense, and at some point it becomes so dense that CO becomes so not dense that at certain radiuses CO is just completely photodissociated, sorry, and does not exist, and therefore that would decrease your R90. And when I first read it, like, it was a bit inobvious, because this is constructed analytically from this, and where is chemistry here? This is not obvious at all. But the chemistry exists in the value of R90 and in the fact that it does not depend, quote unquote, does not depend on RC. It does depend on RC, depending on the mass. But for this formula it doesn't. the chemistry is in this, and apparently this is for the dissociation chemistry. But they say that you should take this with a grain of salt, because in all of their models they have not obtained an R90 that is lower than characteristic radius. And with this plot it makes sense, because they go only up to 65 AU, and this is somewhat here. And as you can see, for these masses the threshold is not, like the maxima is not over, they have not gone over the maxima. But they consider lower masses, and I checked for these lower masses this analytic formula, and 65 for those masses is after the maxima, so they should have gotten, according to the analytic formula, an R90 that is below their R characteristic radius, and yet they haven't. Why? I don't know. Because they have not shared their chemistry or anything. And again, it is constructed on the approximation that well fits lower masses. Although you can see that there is a bit of variability actually here for RC, which they also choose to ignore. But at least for this, and there is like a very good fit. But I guess maybe because it's yeah, maybe that's the problem, that it's not very well fit when you consider different RCs, but this dependence is constructed upon this dependence that has a very particular RC, because this is based upon the RC 60 equals 65, but which again, if it's 65 for the lowest mass models, it should have been over this maxima, and they should have gotten a lower R90 than RC, and yet they haven't, but it is still well fit by this approximation. I don't know. This is, and they don't comment on this that much. So this is a bit of a black box. And this plot here is just it's different density profiles, column density profiles for different values of RC, and it just shows that if you consider a certain value of R90 and certain column density at that value, you get two solutions, and the values that they took apparently correspond to this object. Okay. Lastly, what they did is they decided to apply their results, and they took a number of samples of disks that had R90 measured from a range of star-forming regions. So, for example, in Lupus and Taurus, D-sharp, I don't remember which constellation that is, and Upperscope. So there are the plots of the distributions of R90 in those samples, and what they did is they needed also disk mass to do that. What they did is, apparently all these disks had dust mass measured, and they just multiplied that by 100, classical estimate, classic relation between gas and dust mass. And this all had uncertainties, and they just drew different values from these error bars to create for each object a distribution, an uncertainty for characteristic radius, and then based on that they did their own statistics on the objects. And to be honest, in our models, R90 are a bit closer to characteristic radius, and for me it's a bit crazy to see such small values, but that's the result. And like 5AU, characteristic radius, is a bit crazy to me. Oh, there's also like characteristic radius that goes up to 0.1. What the hell? Anyway, yeah, but they also note that that's strange, right? This is such a small value, but not because it's a small value, because it's smaller than others. And for upper scope, there is an estimate of age, and it is older than other star-forming regions. And this kind of goes against the predictions, theoretical predictions, because theoretical models of evolutions of viscous disks and wind-driven disks tell that characteristic radius should not have changed. No, what am I saying? Should have at least increased or have not changed. So if it's a wind-driven disk, it shouldn't change. If it's a viscously driven disk, it should expand. And yet, upper scope, an older system, disks smaller. The way they explain it is that upper scope is close to OB association. The star-forming region is close to OB association, so it's full of very massive luminous stars with powerful UV emission, and this could be an environmental effect. Basically, that these disks could have experienced external evaporation. This could explain it. But I'm also, like, when I was preparing for this review, I also thought that, so when they derived these estimates for characteristic radius, they considered only the smaller value out of two solutions. But they could have considered for upper scope a larger value, and that would have aligned then probably with they actually don't for some reason they don't say it, like as if they haven't considered it at all. I kind of understand why, because they don't trust it, because in their models they never got an R90 that is more than characteristic radius. But if you think about it, it would align, kind of. It would kind of make sense that yes, they're actually, characteristic radius is actually larger, but R90 is smaller because photo dissociation. So, but they have not considered it at all. They just explain it by external photo evaporation, which could also be the thing. Otherwise, and they kind of do this conclusion about upper scope only when they've derived RC, but I think you can actually see that R90, on the level of R90, they're also systematically below other disks. I guess why they don't want to talk about R90 is because it's a more like less fundamental parameter than characteristic radius, like it's so tied to CO, whilst characteristic radius is more of a like tied to theory thing that is evolution of which was predicted. That this prediction for that the disk should expand was given for characteristic radius, not for R90, so we don't actually know how R90 would behave, right? So I guess that's why. But in the context of this paper, that's kind of the same thing, to be honest. Especially if you consider only like one of the two solutions. And you can see it in these distributions, they're basically just the same, just the values are divided by a certain factor, and that's the only difference. But okay. Then what do they discuss further on? So the first 2 points are related to this derivation of RC for the samples of the disks. Is that first thing of uncertainty is that there could be binaries. And binaries, and disks around binaries evolve a bit differently. And in their model they considered only singles. So there could be some wrong estimates based on that. And also different methods of R90 estimation were used in different samples. So you can go kind of 2 ways about it. One is you could determine R90 from an image, and the other you can do it directly from the visibilities. So the image, I think, I haven't read these papers, but I think most likely, given that it's CO radio transition, it was observed by an interferometer, most likely ALMA. So you get visibilities from ALMA, from interferometry, and you then reconstruct an image. And you can do R90 after recreating an image, or you can do it directly from the visibilities. I suppose in this paper, since they synthesized an image and have not simulated observations on an interferometer, they were just doing it from the image, and that could have affected things somehow. Then more modeling points of discussion is that while they throughout the paper assume a standard gas to dust ratio of 100 mass ratio, so the gas component is 100 times more massive than the dust. This may not be entirely true for the entirety of the disk. This is a value that could vary, especially if you consider dust settling and stuff, and other different effects, dynamical effects, which are not considered here. As far as I understand, it's kind of a static model. Then there is a bit of uncertainty about CO abundance because of effects that they could not have included, and because of, for example, other dynamic effects that they have not included, like vertical mixing, when technically, again, if you consider CO and your disk is massive enough, you see only surface, you don't really care about what happens underneath. What is frozen out, it doesn't really affect an emission anyhow. But if you have mixing, if you have stuff going up and down, that should affect your abundance and should affect your surface abundance, and therefore affect your emitting surface. And they don't have that. This is also creates a certain takes away some truthfulness to their result. And then largely there is, of course, an uncertainty about the density and temperature structure. With density, there is a question about both radial structure and the vertical structure. So with the radial structure, we have this prescription that comes from the theory, right? But it's kind of difficult to test with observations if it's really the density that is there, because you don't really infer it from the observations directly. You can try to fit the model to the observations, to some kind of try to fit it to some observational characteristic, and but usually there are so many parameters in the model that you can kind of fit anything if you want. That's that. So, you know, even if you have fitted successfully something using that density distribution, that would not really guarantee you that it is the density distribution. So it's a bit hard to tell what is the density distribution there. And with temperature, the problem is that it's kind of connected to vertical structures. They prescribe a vertical structure, assuming that it's either isothermal vertically, when it's not. And they don't actually get this isothermal. When they compute temperatures according to the structure, they don't get one temperature along the z-axis. So there is also that. That can also affect the results. So that's their concerns, the concerns that they've raised. There's also another half of the paper that is appendices. I will not go over that, although I have told some stuff from there. But overall, this is just flavor stuff that I'm not really interested in discussing. What are my major critiques beyond what I've told already is that, so this result that we've got, this connection of R90 and RC, they do feel very model dependent. And I, for example, would not use that for my, I mean, I've even tried, you know, I've computed my dependence of R90 versus RC and theirs. It did not match at all. So I already know this is a model dependent thing, because our model does not reproduce that. And we don't, and beyond that it's not model dependent, we don't really exactly know what's inside the chemistry of that model. So we can't even really reproduce it unless we take the exactly same model from them. If it's openly available, I haven't checked. And yeah, and the fit relies on lower masses and doesn't give enough weight and attention to observationally relevant masses, which are 10 to the minus 3, from 10 to the minus 3 to 10 to the minus 1. There can be even larger disks than that. It's just that if disks become larger than 10% of the star mass, they tend to become self-gravitating, and it also leads to a bunch of dynamical effects like gravitational instability that static models don't really cover. So, for example, we in our model, which is also dynamically static, don't go down that road because that would not be exactly correct, a correct description of a disk. They don't do that either, I suppose, though they don't even have star mass here. They don't need it in the context of this work, but you know, but yeah, although it needs checking because they consider luminosities, pretty low luminosities, and that could correspond to pretty low mass stars, and yet they still consider disk mass of 10 to the minus 1, which, although we do that too. never mind, I'm not going to critique that. But yeah, this is like a dangerous category when you go above 10% with a static model. You shouldn't do that. Don't do that. I mean, you can, but tread carefully. So yeah, there's that. Now on to conclusions, to finalize this. review. So first thing they say, they found an empirical correlation. Strong words. How is it empirical when it's all based on models? I don't know. And importantly, this correlation does not significantly depend on other parameters. What happened to the section when they talk that it depends on luminosity, gamma, and interstellar radiation field? I don't know. Maybe the whole thing is inside significantly. What do they consider significant? I don't know. Then they created an analytical prescription, the connection, great, nice idea. Then analyzing analytical prescription, they found that there is a maximum R90 for a given M disk, and there are two solutions to a given R90 and M disk. And lastly, they have applied that to 4 samples of disks, found the median values, cool, and yeah, the note about upper score, which is very small, and this decrease in RC for the older region goes against predictions of both viscous, and wind-driven evolution. That's it. Thank you for listening. I hope you liked it. I don't know how long it took, probably an hour. Anyway, thank you.